Okay, so section 13.5 deals with curl and divergence. And, you know, these concepts, how are they important? Well, one thing we learned about the curl is that it can be helpful in telling us if we have a conservative force field for a three-dimensional force field. So in section 13.3, you had a criteria that would tell you if a vector field is conservative, but it was for vector fields in two-dimensional space, where the vector f was equal to p times I plus q times j. But what if you have a vector field in three-dimensional space? Well, you need to have a new criteria to determine if the vector field is conservative. And we learned that the curl of the gradient of a function f, and the gradient of a function is itself a vector field, right? The curl of a gradient of a function is equal to the zero vector. So if, for instance, if this vector field f, if we could show that the curl of this vector field f was equal to 0. Okay, if we could establish that, then that means that the vector field f would be equivalent to the gradient of some potential function f. And it would be worthwhile looking for that potential function. So that's how, with a three-dimensional vector field, that's how we can establish if that three-dimensional vector field is conservative or not. Because if the three-dimensional vector field is conservative, then naturally we would want to use the fundamental theorem of line integrals to compute the work that that vector field does in moving a particle from one point to another point in the field. Okay, I mean, the fundamental theorem of line integrals is extremely useful and helpful. But if the vector field, sometimes what happens is a student will be presented with a vector field, like in homework or on an exam, you know, they'll right away look for a potential function for that vector field. But if the vector field's not a conservative vector field, then it's a waste of time to look for a potential function, because there is no potential function. So it's always important, before you compute these work kind of problems, to see if you want to use the fundamental theorem of line integrals, check to see that you have a conservative vector field first. And if you don't have a conservative vector field, then you have to compute the work the old-fashioned way, using the definition of the line integral of a vector field, which you learned back in section 13.2. Okay, so for this particular problem, what we did to see if it was a conservative vector field was basically computed the curl. And we learned that the curl of a vector field f was equal to the cross product of the del operator. This is the del operator with that vector field f. And so we worked it out. This is the determinant of a 3x3 matrix, and we worked it out. And it turns out that this curl was equal to the zero vector, and so that vector field f was a conservative vector field, and therefore it would be worthwhile trying to find a potential function for that vector field. Are there any questions so far? This is just kind of a quick review of what we talked about at the end of our last class. Are there any questions? All right. Well, all right. So we've seen a use for curl. We've seen a use for finding the curl of a vector field. And there is an interpretation for that as well. So let me bring up the ebook here. Okay, and why do they call, so remember, maybe I'll just point this out. Let me go back here a little bit. Hold on here. Yeah. So the definition of the curl was a fairly complicated definition. That was, oh, hold on, let me get this down. Yeah, that was complicated to remember. But what we did was we were able to show that the curl of f was equal to the cross product of the del operator, which is the operators from the gradient vector, with that vector field f. And so that's how we compute the curl. And again, that example that I just talked about, we computed the curl that way. And you have that in your notes. So physically, what does a curl mean? What does a curl mean? Okay, well, the reason, and I'll just kind of get my little marker out here, hopefully be able to highlight this. Okay, so the reason for the name curl is that the curl vector is associated with rotations. Okay, the vector field f, if the vector field f represents velocity field and fluid flow, if we have that as our vector field, you know, vector fields can represent gravitational fields, they can represent electrical fields, velocity fields. If the vector field f represents a velocity field, then the particles near XYZ in the fluid tend to rotate about the axis that points in the direction of the curl. Okay, so that's what they have below here in figure 1. Okay, so here you have a point XYZ, and it's located in a vector field f, a velocity field, and the rotation, look at how in figure 1 at the rotation of that field, and the curl vector, which is a vector, forms an axis that the particles rotate around. And if you think about the right-hand rule, that's right, Eric. That's right. It is kind of similar to a torque problem. If you think about the right-hand rule, if you take your right hand and curl your fingers in the direction of the way the fluid's flowing there, in the counterclockwise direction, then your thumb will point in the direction of that curl vector. Okay, so, and the length of the curl vector is a measure of how quickly the particles move around the axis. Okay, and so this is just, you know, this is true. And they note that if the curl of your vector field f equals the zero vector at a point P, then the fluid is free from rotations. And we call the vector field f irrotational at P. In other words, there's no whirlpool or eddy at that point P. Okay, if the curl of the vector field equals 0, then there might, like if you were to put a little paddle wheel about that point, the paddle will move with the fluid, but it doesn't like rotate. Okay, and I'm going to do an example to sort of help you see this kind of thing. This is going to come up again when we learn about Stokes' theorem, section 13.7, which will be next week. We learn about Stokes' theorem. Well, actually, we might learn a little bit about it on Thursday. Okay, but are there any questions so far? Any questions at all? Hold on here. Okay. All right. Well, then let us continue on. This section deals with what's called curl and divergence. We haven't learned about divergence yet. Okay, so again, you have a vector field F that has I, J, and K components, P times I plus Q times J plus R times K. The divergence of the function is equal to the sum of these three partial derivatives. How does the P component vary in the X direction? How does the Q component vary in the Y direction? At what rate? And what is the rate of the R component varying in the Z direction? So the sum of these rates is called is equal to the divergence of the vector field. And observe, they mentioned below, observe that the curl of the vector field F is equal to a vector field, but the divergence of F is a scalar field. Okay, and if you want to have, like, the curl of a vector field F is the cross product between the del operator and the vector field F, we can express the divergence of the vector field as the dot product of the del operator with the vector field F. Okay, now again, it's the del operator. I mean, a dot product means you're multiplying the components of two vectors piecewise, right? And you can think of like the partial with respect to x times p, plus the partial with respect to y times q, plus the partial with respect to z times r. That gets you the divergence of f. It's just another way of thinking about it. Okay, are there any questions on that? Okay. Well, so computing divergence. Okay, so in example 4 here, they give a vector field F, okay, right there, and they want you to find the divergence of that vector field F. So by the definition of divergence, the divergence of that vector field F is the dot product of the del operator and the vector field F, which is really just the sum of those partial derivatives. Okay, so take a moment to look at it. One moment. Okay, are there any questions in general on this? I just wanted you to look at it. I didn't want to like formally, you know, verbalize what it's saying there. Are there any questions on how to find the divergence? Who's feeling good? Who's feeling good so far? Maybe give me a few thumbs up if you're okay. Good, John. Good, Eric. Good, Ryan. Good, Robin. Excellent, excellent. Okay. Okay. Well, then, is there a physical interpretation for divergence? There is. There is. Let me go down a little bit here. Yeah. So, fluid flow. Fluid flow. Okay. So, the reason for the name divergence can be understood in the context of fluid flow. And I always think of my father when I do this section because he was an expert on fluid flow. If you have a vector field F that is, say, the velocity or fluid of a gas, that divergence of that vector field F represents the net rate of change with respect to time of the mass or fluid of gas flowing from a point per unit volume. In other words, think about divergence. I think of it, divergence is the sum of three rates, okay? And the divergence measures the tendency of the fluid to diverge from a point, okay? And they also say here, I think they left something out here. If the divergence of F is equal to 0, then the vector field F is said to be incompressible. Incompressible. And again, another example of this, an example showing this would be helpful, a concrete example. And I'm going to show you that. So what I want to do, I want to just point something out here before we get to that example. So there's a lot of advanced stuff that's going to come up in more advanced physics from this section regarding this del operator, but I want to keep it kind of, I want you to take a look here at this vector form of Green's theorem. How many remember Green's theorem from the last class? Okay, we learned it. Robin remembers it, and of course, you'll have some upcoming homework on Green's theorem. But what Green's theorem is if you have a particle that moves along a closed path in two-dimensional space, Green's theorem allows you to compute the work that the vector field does in moving that particle once along that closed path. And the Green's theorem, okay, you have it right there, right in front of you here. I mean, there it is, the Green's theorem, which is really the sum of two line integrals, one with respect to x and one with respect to y. But what we can do is we can write the Green's theorem in a little bit more convenient way, in what's called vector notation. Okay, so take a moment, just look at that for a moment, and then I'm gonna go over this, but I want you to look at it for just a moment. Okay, and so you can see what they're doing here. The curl of a vector field F, okay, that has like I'm talking right here now. This vector field F is a two-dimensional vector field. So you got the P and the Q components, but the Z component is 0. So if you do the curl of that vector field, and that's the del crossed with the vector field F, you're just going to get the partial of Q with respect to Z minus the partial of P with respect to Y times the vector K. Let me just see one thing here. Yeah, that makes sense. That makes sense because the partial derivative of P with respect to Z is equal to 0. Now look what they do. The curl of the vector field F, if you dot that with the vector K, okay, you're just going to get the difference of the partial of Q with respect to X and the partial of P with respect to Y. Well, that is just the integrand for the Green's theorem. Okay, so in other words, Green's theorem can be written in this nice form, and that's called the vector form of Green's theorem. Okay, that's called the vector form of Green's theorem. Has anybody maybe? I doubt you would have seen that yet because you, but I don't know. Has anybody seen that maybe in another class? All right. Well, of course, you're taking this class, and so you'll see it in the future. But you know, it's just kind of a nice, compact way to represent the Green's theorem, and I just thought you should see it. Okay. So what I'd like to do an example here. Let me just bring it up. One moment. Okay, I have it in my thing. I just got to upload it here. So one moment. Let's see. Thank you for your patience, everybody. Thank you for your patience. This would be like me in class looking for my notes on something, right? So let me see here. This is it. Curl and divergence. Let's see if I can give you a more, like just an example to give you an intuitive feel for. I mean, you do know what the book says, but let's see if we can apply it to an example. So it's uploading here. Thank you for your patience. There we go. Okay, this is what I want. Okay, so I want you to take a moment and copy down this example. Even draw the direction field in your notes. Okay, and then we'll talk about this example. Okay, so take a few moments. Okay, so let's take a look at this. So this is a vector field below. We have a picture of it. And we're assuming that the z component of the vector field is 0. So it's a two-dimensional vector field. What seems to be happening to the vectors as they move outward from the origin? What would you say about the field? If this were like fluid flow, does the flow seem to be getting weaker or stronger as we move away from the origin, based on this picture? Definitely getting stronger. That's right, Robin, Diodath, and Christopher. Very good. Very good. All right. Now, does it appear on the field, if we were to just put like some, little, I don't know, a little piece of paper or something in the field, if we were to put a piece of paper or like a leaf, think of wind and a leaf or something, a leaf in the field, but let's say a piece of paper, would the paper rotate in this field? Yeah. Well, so Christopher, you're right. The paper, it doesn't appear to be rotation here. Okay, I think of like a little, I don't know, little rubber ducky, in the bathtubs, the little rubber ducky. If I put a little rubber ducky on this field here, the rubber ducky is just going to move out. It's not move away from the origin. It's not going to turn or rotate. So it'll move out. It'll move out, but it's not gonna rotate like in an eddy or something like that. You're not gonna have the particle be swirling, swirling around and around and around and around and around. It's not going to be swirling in this field. Are we in agreement on that? All right. So I'm not saying, yes, I'm not saying that I want to say it's the right way. I'm not saying that the divergence of the field is equal to 0. I'm not saying that. But it appears that this vector field, the picture of it, it appears that the vector field is irrotational, because an object in the field isn't going to rotate around and around and around. So that might lead us to believe that the curl of the vector field might equal 0. Now the divergence, well, we'll figure that out. But are there any questions before we move forward? Does everybody have the picture, the example copied down all right? All right, maybe give me a thumbs up if you're ready to move forward here. And we'll move forward. Okay, John's good, Ryan's good, name is good, excellent, excellent. Okay. So, okay, divergence, how would we think about divergence? Okay. How are we going to think about divergence? Well, I'm going to focus on like one layer of, I can look at different layers, right, of the fluid for different Y values and study how they behave. I'm going to look at this first layer to help me. So on the next page, what I've done is I recognize that the force field F, vector field F equals pi plus qj plus 0 times k. And I've drawn that first layer of water, so to speak, near the x-axis. Okay, and based on the picture, and the picture, this is just one piece of the picture, but at least based on that picture, P seems to increase with x, but Q does not increase with x. So let me just give you a moment to copy down up to like here, okay, and then we'll talk about it, okay. Okay, so what defines these vectors in the vector field? Well, there are two components. Okay, there are two components in the vector field. Okay, there is a component P and a component Q. Now, does P control the horizontal part of the vector or the vertical? Is P the horizontal component of the vector or the vertical component of the vector? Whatever that function P is. That's right, Ryan. P is the horizontal component of the vector. And if we study this one set of vectors, we're studying the vectors as x increases, okay? Because you know, based on the picture here, I'm studying how these vectors behave as x gets larger. Well, what seems to be happening to the horizontal component of the vectors here with x? So, I mean, I guess I could, maybe to complete the picture here, it won't hurt to put an x-axis, right? What's happening to the horizontal component of the vectors as x increases? Is the horizontal component getting larger are getting smaller. It's getting larger. They're getting longer. The vectors are getting longer as x increases. So this means then that p has to increase with x. P has to increase with x, which means the partial derivative of p with respect to x is positive. Okay, now actually, well, are there any questions? Are there any questions at all on that? Okay, well then let's now focus on Q. Let's focus on Q. Okay, so the Q component here. Okay, does Q component control horizontal, the horizontal part of the vector or the vertical part of the vector? Is it the horizontal or vertical component of the vector, that component Q? It's the vertical part. That's right, Robin. And so as x changes here in the picture, does the vertical component change at all? I mean, what is for these four vectors, what does the vertical component basically equal? That's right, Christopher. No, what is the vertical component equal to based on the picture? It equals 0. So in fact, Q does not, I shouldn't say not increase, it does not change. It does not change with respect to x. And so that means the partial derivative of Q with respect to x equals 0. Now the R are there any questions on that? Okay, okay. Now, incidentally, why am I finding these partial derivatives? It's because the curl and the divergence of the vector field is based off of partial derivatives. The partial derivative of R with respect to x would equal 0 because the z component is 0. Okay, and now what I'm going to do is I'm going to now, and I want to comment too that that if I go back to the picture here, and I look at, for instance, the second layer of vectors, it's similarly true that the partial derivative of p with respect to x is positive because those vectors are getting longer in the x direction as x increases. But the partial derivative of q with respect to y with respect to x still equals 0 because the vectors are not getting any taller as x increases. And it's true for every layer. Okay, but now what we want, so in general, we can say the partial derivative of p with respect to x is positive. The partial derivative of q with respect to x is 0. And the partial derivative of r with respect to x is 0. But now what we want to do is we want to study how the vectors behave in the y direction. Okay, so what I can do is I can look at this first set of vectors here. How do those vectors change with respect to y? Okay, so what I do is I say, okay, here's that. Here's a kind of a picture of that. And in this case, are the vectors getting longer in the x direction as y increases? And I guess I can probably should draw a y-axis here, shouldn't I? Just to be complete. Well, in fact, well, I meant, Christopher, that yeah, the partial derivative of p with respect to y is 0 because the vectors, the width of them, the horizontal width of them isn't changing as y increases. But the vectors, the vertical, the heights of the vectors are increasing with y, and so the partial derivative of q with respect to hold on. The partial derivative of q with respect to y would be positive. Okay, so you see how this works? I'm doing this carefully because it's you'll have a multiple choice question in your homework on this kind of thing, and who knows, maybe the final exam too. And you know, this kind of question is kind of a one-shot deal to get it right, for obvious reasons, and I want you to do it carefully. The partial derivative of r with respect to y would equal 0. Okay, and so now we have six partial derivatives, and there are only three more left. Well, p and q don't vary in the z direction, so the partial derivative of p with respect to z would equal the partial derivative of q with respect to z. They both equal 0. And now also remember the partial derivative of r with respect to z also equals 0. Okay, so just kind of doing it step by step. And with this analysis now, we have enough information to answer the question at hand. So I'll go to the next page then when you're ready. Just let me know. And please let me know if you have any questions. Okay, Ryan, Robin, and John are good. Okay. Well, that being said, let's go ahead to the next page. So the divergence of f, I mean, this was part A, find the divergence. The divergence of f is the sum of these partial derivatives. And we know that the partial derivative of p with respect to x and the partial derivative of q with respect to y, they're both positive, right? They're both positive. And so the divergence is greater. The divergence of this vector field is greater than 0. And intuitively, that would make sense because the net rate of change is positive. Okay, divergence measures the tendency of the fluid to diverge from the point. The rate of change is, as you go out from the origin, the flow is getting greater. So divergence is positive. And the curl, Well, we've established what all those partial derivative vectors are, so we can get the curl, and we show that it equals the zero vector. And that supports the idea that we thought originally, based on the picture, that this fluid is irrotational. It is irrotational. So fluid flow is a huge application of these, later sections that we're covering. It's a bit, and I'll tell you, I think this is just some of the most beautiful math, around. I hope you like it too. But all right, let me know when you're done copying. Let me know if you have any questions. All right, are there any questions at all? Okay, I want to stop for a moment